Okay. Hello, my name is Amir Mohammad Mirzaei. I'm a PhD student at Politecnico di Torino, and I'm going to present a new model to estimate finite fatigue life of notch components. I will start with an overview of the model, then I present the model, and I validate it with three different sets of experimental data, and I finish my talk with conclusions. To start, let us consider a ascent curve. It can be divided into several regions, for example, low cycle fatigue, high cycle fatigue, or finite life or infinite life. In the middle, there is a region that can be captured by a line, which firstly proposed by Basquins, and you can see here. Another assumption that I'm going to use is that I assume that the stage 2 is the dominant stage during the fatigue, so I can use the mode 1 relationship. And the final one is that I assume that the size of the plastic zone is negligible, so I can use linear elastic mechanics. The model that I'm going to develop is based on finite fracture mechanics. As Arturo said, it's firstly proposed to determine the failure load under static loading condition for brittle materials. As you can see here, it contains two conditions. First, stress condition, and the second one is the energy condition. And the material properties that you need to capture the failure is the sigma u, or ultimate strength, and fracture toughness. The model was extended to fatigue limit by Sapora et al. The idea to extend this model for finite fatigue life is to vary the critical material parameters, sigma c and K1F, which we call it critical cyclic stress and stress intensity factor at failure. We assume that these parameters vary as a number of cycles, and their behavior can be captured again by Basquins equation. So as soon as we have these two material properties, we can insert it into the system of equations by finite fracture and determine the finite life and the critical crack advancement. Similar to the static case and the fatigue limit case, sigma c can be determined using plane samples and K1F with the crack samples. And in case we don't have a crack sample, we can use inverse calibration using a notch geometry. Here you can see a procedure of the model. So the first set of experimental data that I used to validate the model consists of different notch geometries, and the material is steel, and the loading condition is R equal to -1. It's tension compression loading condition. Here you can see the related SN data for the notch samples. And here is the estimations by the model. In the vertical axis is the number of cycles to failure by experimental data, while the horizontal one is the estimations. If a data is on this solid line, it means a perfect estimation. And these two lines represent the scatter band of 3. As you can see, the predictions are quite satisfactory for all the notch geometries. Here is another set of experimental data. It's the same notch samples as the previous set, plus two new samples under bending condition. Note that, please, that loading ratio for this set of experiments is equal to 0.1. As you can see here, the estimations here are more or less good, but it's not very satisfactory for the bending test. This can be justified by the fact that SN data are dependent on the loading condition, because I determined sigma c and K1F based on the tensile samples, while I use them for the bending cases. And the last set of experimental data that I'm going to present is based on the this set. It contains two different notch geometry and a notch sample with and a semicircular notch sample. The material here is in Cornell made by selective laser melting. Here we compared the model by theory of critical distances. The left side is the predictions by finite fracture one, and the right side is predictions by theory of critical distances. And as you can see, the predictions are quite satisfactory. So to conclude, we propose a new failure criterion, for finite fatigue life of notched component. The idea was to vary the critical material parameters, stress intensity factor, and the strength by the number of cycles. And we captured this behavior by the Basquine's equation. Comparison with the experimental data showed the soundness of the model, but still the work is ongoing. Here are the references of my presentation, and thank you so much for your attention.